This is section 3.1. We'll be doing it today and tomorrow. We have left behind the shortcut. We've left behind, I should say, the limit as h tends to 0 or the limit as x tends to a, right? The long way of getting derivatives, they're done. From this point onwards, we will do derivatives using shortcut methods. And the only shortcut method we know right now is called the power rule. And we are going to use it and get as much mileage out of using it as possible. So we are going to use the power rule, the shortcut method, to differentiate polynomials, simple square roots and cube roots, simple fractions like 5 over x squared, various expressions, but simple ones. A new guy that we haven't done, and he won't be the power rule, but we're going to find out how to differentiate e to the power of x. Remember the exponential function, e to the x, how to differentiate that. That would be a one-off thing. More complicated expressions. And then we'll do some find equation of tangent lines and a new guy called equation of normal lines. And we won't get to these guys until tomorrow. Right, we've done some of these before, so let's jump right into it. Polynomials. 4x to the 5 minus 7x squared plus x plus 1. Power rule. That's how you would do these. Multiply by the power and reduce the power by 1. So the derivative is multiply by the power, right, and reduce the power by 1. Multiply by the power, reduce the power by 1. Things like 6x and plus 1, technically they are the power rule, but it's easier just to do them as special cases. Won't plus 6x always get you plus 6? And what about the number like plus 1? What do you get when you differentiate plus 1?
0 or nothing there?
0. Just none there. Have we done enough polynomials that I don't need to do any more of these? So you feel comfortable about multiply by the power and reduce it by 1 for polynomials. We pretty much covered those. So if we're good, can I move on? We've got lots more you guys to do. Okay. End of polynomials. Going to spend more time on rational. We haven't really done that many of them, so I think it's important that we do maybe some more. Let's have 4, the square root of x. Nice simple one just to get into the swing of things. Now, you're going to be able to use the power rule, but you have to write it, this guy here, you have to rewrite it as a fractional power so that you can do that. Now, a square root is a half power. So 4 square root of x is the same thing as 4x to the half. Now I can use the power rule. The derivative, I'll use y dash notation. Multiply by the power and reduce the power by 1. And now we have the style point rules. And the style point rules, especially for what we're doing right now, the one we're going to be using a lot is make it look like the original. That does not look like this guy, not even close. So I have to do some algebra things that we picked up from Math 99. Are you comfortable with a negative power is the same as the thing on the bottom with a positive? So x to the negative a half is that guy. And secondly, aren't fractional powers the same as, in this case, square root? So this is the final answer. Are we good? Now, let's show you a different kind of rational question. Let's do f of x equal to 7x to the power of 3/4. Now that is also irrational, expression, a radical, I should say, expression. It is already actually written in the format that we like, because this version is easier to differentiate, because I can just immediately multiply by the power and then reduce the power by 1. Right? 3/4 take away 1 gets you -1/4. Now, style points. There are two schools of thought about what that guy there should be written as. This fella or this fella. Now, they are both correct, and neither of them is more correct than the other. Me personally, I like this one, but you may find in different textbook, if you go hunting for them, that they may do that. Just do that one. And the reason why I'm going to accept that one and why I believe it's a better version is, remember, the rule is you should look like the original. Isn't that just a fractional power, just like that is? Now, the fact that it's negative is not that big a deal, so it's okay. Some people say, it is negative, it is a big deal, so they write it like that. But I don't think it is a big deal, and I'm not the only person who believes that. So less work, just leave it like that. Are we good? Let's show you, a more complicated one. And let's stop using x's. Everything's x's. How about y equals the cube root of v to the 4 plus 4 over the square root of v. Now, these guys contain square roots and cube roots, so that makes them radicals, but they are nowhere near written in a format that's going to let me, use the power rule. Right, this one. What fractional power is the cube root of v to the power of 4?
V to the 4/3.
Agreed. It's a funny looking 4, but it is a 4/3. The cube goes in the bottom, the cube root goes in the bottom, the 4 goes in the top. Now, this one here might tax you. 4 over the square root of v is a fractional power. It's a negative fractional power. What is it?
1/2.
And that version of 1/2, right? -1/2. If you want to see what that might look like, this is what I'm doing. I'm saying that guy is that guy, which is that guy. Okay. Now, why do I need that? If you are going to use the power rule, don't you need powers to do it with? So things have to be written in fractional format. Now I can do the derivative. Multiply by the power, reduce the power by 1. Multiply by the power, reduce the power by 1. Now, in this question here, I left it. And the reason I could leave it is because it looked like the original. This guy, I cannot leave. Do you notice that it doesn't look like the original? So the style points of this one are going to be much messier. This fella here, for instance, is now the cube root of v, right? V to the 1/3 is the cube root of v. This guy here is a kind of two-stage thing. That line just takes care of the fact that it used to be negative. And that fella is the square root of v cubed. Now, when you look at a question like this and how we got the answer, the stage from there to there, that step there was calculus. That was where we found the derivative. It wasn't the step to get from there to there, and the step from there to there, and the step from there to there. Weren't all these algebra, right? Doing various things in algebra, either to get it into a form that allowed me to differentiate it, or after I've differentiated it, getting it back into the original look, so it looked like that. So you'll probably spend more time doing algebra than you will be doing differentiation. Most of the time, differentiation happens in a line. Right, one line is done. And all the other stuff is, you know, making it pray, right? Getting it into form that's needed. Do you want to see some more rationals, or are you good with these guys? Good with these guys? Okay.
Good.
Let's look at number 3 then. Rational functions. And what that we're talking about here are simple ones. So I'll give you an example of that. Here's an example of a function with fractions. Rationals are just fractions, right? Old name for fractions. And I want to differentiate it, and I'm going to use a power rule. But of course, I'm going to have to do some algebra, because if I want to do that, don't I have to write it as powers of x? And we've actually kind of done this already in one of the earlier questions. But just to remind you, isn't 4 over x cubed x to the negative 3? And isn't this guy 2x to the negative 1? Can you see how the power rule can now be used? Multiply by the power and reduce it by 1. So that means I can differentiate things that look like that now. And its derivative, multiply by the power, reduce its power by 1. Right, take away 1, you get negative 4. Multiply by the power, so it's now positive. Reduce the power by 1. Do you think that's the final answer, or do we have some style points? Final answer or some style points?
Style.
Yeah. Okay, won't this guy return to being a fraction? And won't this guy return to being a fraction? Now you're finished. Are we cool with simple rational functions? Do you want to see another one of them, or does that process seem pretty much, you know, kind of what we've been doing anyway? I'm good to move if you're good to move. I need kind of nods, or could we see some more? I'm good both ways.
I want to see one more. That's okay.
Okay. Let's change the letter of the alphabet. Let's change the variable as well. G of W. How about 2 over W squared plus W cubed minus 4 over W 4. So I want to differentiate that expression. It's got 2 fractions and 1 polynomial, but it's okay. You can have mix and match. This fella will have to be converted to a negative 2 power. W cubed is good, so I won't do anything to that. And this one will be turned into a negative 4 power. That means I can now differentiate. Multiply by the power and reduce the power by 1. Multiply by the power, reduce the power by 1. Multiply by the power, and reduce it by 1, and then do some style points on those pieces that need it. This piece needs it. That piece is okay. And this piece needs it. When you're using the power rule, do you see that even although the context might change, isn't the general process pretty much the same? If you have to, write it as a power of x and then use the power rule. And then at the end, make it look like the original. Very vague way. Isn't that what's happened in every single question we've done so far, right? Write it as some power of x, -2, 3/4, or just 4, whatever it is. Differentiate it using the power rule. And then at the end, make it look like the original. And that's rationals. So number 4, our next situation, are going to be expressions. And I'm going to call these guys simple expressions. So I'm not going to do anything too crazy yet. And we're going to see if we can figure out how you might deal with it. Here's one right off the bat. I want to differentiate that. What could I do?
Start by factoring it out.
Yep. Can you just trust me that if you do FOIL, you get that? That would seem reasonable. And then you just differentiate. And I don't need to do it. Well, let's be purists. I guess I should do that, shouldn't I? It's not much ideal, but yeah, I guess I could do that. Okay, let's try. There are lots of different versions of what I'm talking about here. I want to differentiate that from that ugly expression. I got to figure out what to do. Any ideas? It's not in a form that allows me to use the power rule, agreed? That's my problem. I got to get it rewritten so that I can use the power rule. Does that help in
Did you multiply by
pushing
W
along
squared
maybe?
first or no?
Okay. Yeah, let's try that. Now, if you write this as that, you get that. And we're darn close to something we can use the power rule on. I can use the power rule on this term. A little bit of a tweak. What do I have to do to 4 over W so that I can use the power rule on it? It's not a big deal, but what do I have to do?
Four times W to the 1/2 power. Is that 1/2 or the negative power? Sorry.
It's a negative. So 4 over W gets you 4W to -1, right? That guy becomes this. Right, now I can do the derivative. Multiply by the power, reduce the power by 1. Derivative of that is just -1. And then make it look pretty. Well, it did start life as a fraction, so I should try and at least have a fraction in my answer. And that is the derivative of this. Of course, in some things in math, and the way you started it was exactly right, Skylar, but sometimes in math, there's more than one way to skin a cat. And there is nothing wrong with that method, and it's totally cool and it's good, and use it. I just want to show you another way. Well, maybe someone can tell me before I tell them. Can you think a different way of approaching the same problem? Think of an algebraic way of maybe rewriting this.
Multiply by a fancy one.
Okay, it's a bit quiet, but I did hear multiply, and I'm assuming you said that. Right, a w squared is that. Mathematically, these are the same, aren't they? Multiplying by negative, dividing by a positive. Now, if you multiply through each of these terms, this guy times this will get you 4 to negative 1. This guy times this will get you negative w. And guess what? You're back here. And so eventually the derivative, I'm just writing the answer now. Eventually, after a while, you'll get that. You still have to fill that line in, right? It would fit in here. Just don't want to write it. What's the difference? No difference. It's the same answer, just a different road to get there. Your brain might have worked better. This makes more intuitive sense to you, perhaps. And for some of you, maybe this makes more sense. You pick the method that makes sense to you, because if you do that, you're less likely to screw up. If you pick a method which is, I don't really know how that works, but it does kind of work, so I'm just going to do it and hope for the best, you're likely to make mistakes because you're not really that comfortable with the method. But if, yeah, that makes sense that you can break it apart and get the answers and then do it, then that would be the one. Or, yeah, it makes sense just to bring this up and distribute it. If that makes more sense, that would be the way to go. How about this fella? I want to differentiate it. Let me start by saying you don't need to do a darn thing to that. You can use the power rule. Okay, it's not that often that you get decimal powers, but they are valid. They do happen. They happen in some business formulas. I've seen them. So the world here just becomes apply the rule, even when the things look kind of shady. So 1.7, right, multiply by the power, reduce it by 1. Multiply by the power, reduce it by 1. And that guy is finished. Not all questions are equally hard. Here is a trick question. I am warning you, this is a trick question. Right. Four x cubed plus 7 cubed. I want to know its derivative.
Just 12x squared.
12 squared.
And that is all correct. Isn't 7 cubed just a number? And aren't all numbers 0 when you differentiate? So that includes people putting in plus the square root of 2 or plus 4 squared, or I don't know, minus 1 over 3 squared. And all of those things just numbers, and derivatives of numbers are always 0, even if the numbers are written in ways that might have tempted you to use a power rule. Can you see that some people might say, oh yeah, 3 times 7 squared. Oh God, I shouldn't have said that, because when you tell people the wrong answers, they remember it. Right. Don't do it. Right. The answer is 0. Are we good with at least the simple expressions I've given you? There's lots of variations on what that could look like. But the goal is whatever they give me, I somehow or other have to write it down as powers of x, whether it's negative a half or whatever. I need powers of x. So the next fella is number 5. And we are going to look at how do you differentiate the exponential function e to the power of x. In 141, can you remember doing the guy who looked like that? You probably got it to what, population models, and you did a little bit of algebra with it. You've seen e to the x, right? It's called the natural base, like 2 to the x. E is the base here. This is not, I'll emphasize this, I'll even write it down. It's not the power rule. Don't try and use the power rule, because you'll get an answer, it'll just always be wrong. So we need to know what its derivative is. And the derivative, because I'm telling you, is e to the x. I love e to the x. It's one of the few functions that I very, very rarely ever screw up when I differentiate it. Can you see why it's hard to differentiate, how it's hard to screw up the derivative of e to the x, right? Kind of is, right? So here are some very simple examples. 7e to the x, its derivative is 7e to the x. The derivative of half e to the w is half e to the w. Would you agree you'd have to try really hard to screw up a derivative of e to the x? Right? You really, really would have to be careless. So I just told you that the derivative was e to the x. I'm going to do a pseudo proof to prove to you why it is e to the x. You don't need to know this for a test, but it might just make you feel better, because a lot of people don't like magic. They don't just like being told, this is the answer because I said so and you got to trust me, right? And that's very unsatisfying. A lot of the things that we do that to you, if you do enough math, you can actually prove it, right? But right now, I'm going to try and prove to you that that's true. So, f of x is e to the x. I'm going to use the limit as h tends to 0 of f of x plus h, take away f of x all over h. Now that's the f of a plus h formula. Do you see I'm just replacing the a by x, right? Now, that becomes the limit as h tends to 0. Well, if f of x is this, f of x plus h is e to the power of x plus h, take away e to the x over h. And that becomes the limit as h tends to 0. And I am going to pull out e to the x as a common factor. And for those of you who kind of need to understand why that's allowed, this is what I'm doing. E to the x plus h can be thought of as e to the x times e to the h. Remember, if you multiply things, you add the powers. Can you see that I can pull out the e to the x? And I'm left with that, right? So that's allowed. Now, up to this point, everything is valid. Now the pseudo proof. Do you see this thing here? You can't factor or cancel it or do any conjugates on it. But I can tell you that its limit is 1. And so what you get is e to the x times 1, which is e to the x. So I guess I would have to prove this to you. Now, I can't prove this to you algebraically yet, but if you remind me when we do a guy called L'Hopital's rule, I will show you then. But you can check that its limit is 1. Couldn't I put that into my calculator and find out what it looks like when h is 0? Couldn't I do a table of values like 0.1, 0.01, 0.0001, and I would be able to show you that that answer is darn close to 1, and it gets really closer and closer as I get 0 towards 0. So there's my pseudo proof that the derivative of e to the x is e to the x. Are you comfortable with that? A little bit more than just believing me, right? It is provable. Well, I don't think I need to do any more of these guys. Would you agree there's not that much you can write as far as e to the x is concerned? So let's start playing about with questions that cause some trouble. And let's do that one. Now, if I want to get its derivative, the derivative of e to x is the easy one. X to the power of e. You can differentiate it. And the answer is not x to the e. Isn't e a decimal? Isn't it roughly 2.7128? Right, it's a number. So isn't that a power rule? Right? It's like x cubed, except the number isn't nice like 3. So according to the power rule, you multiply by the power, and then you reduce it by 1. Do you see how weird the answer is? But that's the correct answer. And now, I'll add that again. What is the derivative of e squared?
0.
Yes, you never fell for it, did you? Isn't e squared just a number? And I don't care how you write that number. If you're a number, you're still going to get 0 when you differentiate me. Do you know the most common mistake that people do? Is they call that guy e squared. You know, they say its derivative is e squared, it's not. If I called it plus e, are you even more likely to make the mistake or less likely to make the mistake? Because the derivative is still 0, isn't it? It's still a number. That's 1 in a weird guy. I'll get a couple more. How about this fella? I cannot differentiate things that look like that. Don't I have to turn them into powers? Powers of t, so I can use the power rule, which means I'm going to have to do some algebra on this. What's the square root of 7? It is a number, an ugly number, but it's still a number. 1 over the square root of t is t is the negative a half. Are we comfortable with that? And this guy, square root of 2 is just an ugly number, so it's still the square root of 2. And this fella becomes t is the negative 1. Now that's algebra, right? Are you comfortable with the manipulations that you have to do to get to the power rule? Right? Fractional powers, negative powers, negative fractional powers sometimes. Now, once you get to that point, the power rule takes over. Multiply by the power, and then reduce the power by 1. Multiply by the power, and reduce the power by 1. And that line that goes from there to there is the calculus line. What we're now going to be doing is taking this and making it look like the original, right? What I call the style points. So I got a negative, I got a square root of 7, I've got a 2 and a 3/2. Are you comfortable about how this guy is now that guy? Right. Now, the one next door to it's probably a little bit easier to deal with. Agreed? Now, that guy's finished, isn't he? Got a little bit more, just a little bit more work on this fella. Now, there are a couple of reasons why we push style points, why we expect you to write the answer to a derivative in a particular format. The first one is just consistency. If everybody writes the answers the same way, isn't it easy to compare everybody's working and everybody's results, right? Your result is the same as mine because we both write the same thing, right? And the second, less obvious reason, and that will become maybe more apparent later on, is that once you've found a derivative, very often you're interested in two very specific situations. One of them is, for what values of t is the derivative going to be undefined, which typically means that the function explodes in some kind of vertical way. Now, when I write this question like this, can you see t equals 0 is a bad place to be, right? If you try to get this derivative at 0. Now, if I leave it in, I don't know, if I left it in this format here, wouldn't it be less obvious what the problem was? I mean, you might say, oh, yeah, I'm pretty sure 0 is a bad number, but not so clear. So it allows us to do that. And the two different numbers that we're really interested in is, for what values of t is the derivative undefined? And the second one, does anybody know what the other value of the derivative is? Quite interesting to find. When is the derivative equal to a very specific number? When the derivative is equal to 0. Because when a derivative is 0, that means a horizontal tangent line. And don't horizontal tangent lines often occur at the tops of hills and at the bottoms of valleys? And in many cases, aren't they quite interesting places to know about? Now, in this particular expression, I don't think this helps, but neither does any of the others. But in many cases, you can get both those things if you've written it down in a nice style point way. So for the last few minutes, I'm going to show you a fascinating property about derivatives. Do you know that you can differentiate formula? Here is a formula. Do you recognize it as the area of a circle? Let's By the way, R is a variable, right? Mathematically, it's just the same as that, really, isn't it? They're just called different letters. So, and remember, pi is a number. Now, if I differentiate this guy, you multiply by the power and you reduce the power by 1. Do you recognize the formula 2 pi r? Isn't it the circumference of a circle formula? And you try and think, why would the derivative of the area function be the circumference? Well, one of the ways to think of a derivative is a rate of change. So can you imagine you've got a circle and it's changing, it's getting a little bit bigger, say. Doesn't a circle's area get a little bit bigger by, for want of a better word, a circumference worth of area? So its rate of change is closely connected to the circumference, right, the outside of the shape. There's another one. I don't know if you've ever even seen this one. You should have. Do you recognize the formula for the volume of a sphere? Let's differentiate it. Multiply by the power and reduce the power by 1. Does anybody know what 4 pi r squared gives you when you talk about a sphere? Anybody know what 4 pi r squared is in the context of a sphere?
So the surface area?
It is. It's the surface area of a sphere. I can't draw to save myself, although I'm a visual learner. Can you imagine you've got a sphere and it gets a little bit bigger, right? Like a balloon expanding. Isn't the increase of its volume related to the surface area? Because doesn't it just increase by like a surface area worth of volume? You can take any formula that you know from physics or chemistry or engineering or mechanics or dynamics or whatever science you're talking about. And as long as it's only got one variable here, right, it might be time or velocity or whatever, if you differentiate that function, you will almost always find that it's another formula that you know of from chemistry or physics or dynamics. Does anybody know this formula? Anybody seen a guy like that? It's the formula for the distance traveled in time t, so t is a variable, where the initial velocity is u and acceleration is a. That's what that formula is. If I differentiate this formula with respect to t, so think of u and a and any other letter of the alphabet you want, think of those as just constants. That's like 5t, so you get u, right, when you differentiate it. Multiply by the power and reduce the power by 1, you get that. Do you know this is a formula from physics? This is very often written like that. And this is the velocity of an object with an initial velocity of u and an acceleration of a, and this is going to be its velocity at time t. And I put a t squared there, and I should put just t. So it's v equals u plus at. So when a physics person or a chemistry person or a mechanics or engineer guy, whatever, if they create a formula for something, one of the first things they are probably going to do is differentiate that formula, because it will then tell them the rate of change of whatever it is that we're measuring. And very often that other formula is very useful as well. And so differentiation allows us insight into all sorts of things. And we are finished. So say hi and bye-bye. And I did it with 1 minute to spare. I am getting good at this timing. We learned some cool stuff today. Right, Sabrina? Oh, a thumbs up. Eli, did we learn some cool stuff today? Eli, you're frozen, so I'm assuming that you've went bye-bye already. Okay, unless there's some questions, guys, I am going to close off here.